To start, today the topic is congestion control. Tomorrow we'll have a little clicker test and the lab on distance vector will continue. So the topic today is congestion control. This photograph that I took in Paris from a bridge is illustrating one feature that causes the need for congestion control. It also illustrates how difficult it is for bicycles. You see the poor bicycle path that's in the middle of the intersection. But that's not the purpose. The purpose is to show here one thing that happens. We can view an intersection in the same way as a switch or a router. It has a certain capacity. The capacity is the number of cars that can go through the intersection per minute or per hour. And the capacity of this one is something, but at this specific point in time, no car is going out of this intersection. They're all blocked. It's typical Paris style. They first get into the intersection to discover that they are blocked, and then you're stuck, right? So that you see those cars here are preventing those cars there from moving forward, and those, this one on the left cannot because there's another guy. It's not strictly blocked, it moves a bit. That's the beauty of it. But the throughput of it is very, very small compared to the optimal thing, which would be if you would have very polite cars that would apply the rules that say don't enter an intersection if you are not guaranteed to leave it very soon. So if the intersection is blocked, you should not enter. This causes what is called congestion collapse. Congestion collapse means when the thing is congested, clogged, the amount of work it can create, the throughput, the capacity here is much less than what it would have if it would not be in the collapse here. We will see that this phenomenon occurs in the internet, and this is why congestion control has been developed. Congestion control is implemented primarily in TCP, so expect that next week we'll talk of TCP again. But it's not a transport layer function, it's really a function that has to do with the global management of traffic in the network layer. We'll first understand what the problem is, because it's a bit more complicated than just explaining how TCP works. So we'll explain what is the problem and what are the forms of solution, and in particular what is fairness, and we will compare. That will help us to understand what is the fairness of TCP. Let's start with a small quiz. Here is a toy network of the kind we do in GNS3. In fact, in Lab 5 you will do this one in GNS3. We have two sources, two routers or switches. Here it's irrelevant, the layer at which packet queuing occurs. Assume they are switches if you want. And I assume we have greedy sources, sources that send at the maximum possible rate they can. This maximal rate is, well, it depends on the machine. It can be limited by many factors. It may be the memory channel that is limiting it. But here I'm assuming it's the network access link. So here I assume S2 can send at 1,000 kilobit per second, 1 megabit per second, and this one at 100 kilobit per second. Of course, those are very weak numbers, but this is to make the exercise simple. And assume that's the only control that happens. This is what you have if you have UDP sources, for example, that are streaming data. Of course, they will not stream data faster than the machine can, but they can stream as fast as they are able to. Then the data arrives at first bottleneck here. This router has an output capacity which is 110, which is less than the sum of the two. So there will be losses here. I assume the losses are proportional to this offered traffic. Proportional means this guy is sending 10 times more than this. I assume that the loss rate is the same for both, which means this guy will lose 10 times more packets in absolute number than this one. Whether switches or routers are actually doing that is disputable. They do that if they implement nice smoothing policies. If the queues that exist in the routers are simply first in, first out, then it's a bit random, the amount of data that is lost. But as a first approximation, this is the best we can do. Then it goes to a second router that has two output links. And this output link is at 100 and this one at 10 kilobit per second. And I assume there's nothing else in the network, all the rest is negligible. Right. Question, how much will S1 be able to send to D1? So I assume D1 is the S1 is sending to D1 and S2 is sending to D2. How much will go through? I close in 5 seconds. Aha, so we have the optimists and the pessimists. So the majority believes that there will be 100 kilobit per second that will reach D1, which is the optimistic view. That means you believe things are well organized. There is a grand master that's taking care of everything, God or the IETF or who knows. Because it makes sense, right? If you look at the output, what can S1 send? The max is 100. What can S2 send? The max is 10 because the last link is limited to 10. And 100 plus 10, that works, right? If we do the sum, that goes through the intermediate link. So in the best of the worlds, this is what would happen. But what I have depicted is not the best of the world. It is greedy sources that send as much as they can. So they are like the Paris people that try to get into the intersection and see what happens. Then the correct answer is here. It will be only 10 kilobit per second. In game theory, people call this the cost of anarchy. Here is the analysis to prove this. I analyze first what happens at point number 1. At point number 1, the offered traffic is 1100. The capacity is 110, it's 10%. So here, we will lose 90%. If we lose proportionally for each of the two flows, that means the first flow will have only 10 going through. The second flow will have 100. Then we go to the second thing here. Here there are two output buffers. One buffer here is at 100 kilobit per second, and the offered traffic is 10. So it's fine. We offer 10, the capacity is 100, nothing is lost. So what goes through is 10. And here we have 100 that is offered, but the output capacity is 10, so only 10 will go through. So in fact, what we see in this network, both will send at 10 kilobit per second. They will not send, but the destinations will receive 10 kilobits per second. That's all. So the capacity of this, if we use the information theoretic capacity we saw in the module on TCP, on the transport layer on TCP, would be, with those rules of the game, 20 kilobits per second. Which is stupid, because this network can support how much? 110 here, the sum of those two. This is the weakest cut in this graph. So it can support 110 kilobits per second, but if we let everybody do just what they want, it will support only 20. That is the first drama, or the first take-home message. Being greedy is not efficient, and we could do better. Here the problem was that S2 was sending too much. It was sending more than it could, than is useful, because most of what it's sending is lost, but by doing that it is hurting S1 at this multiplexing point for no value to S2. If we had a mechanism to force S2 to send at 10 kilobits per second, the problem would go away. This is what we'll try to achieve with congestion control in the internet. So first conclusion is, and it's very important to understand on this example, why simply having greedy sources is highly inefficient socially. So if you do an application that is, for example, UDP and is streaming at whatever rate the designer thinks it's good for this application, that might not be a good thing in a network. You might cause problems by doing that. Now let's go one step beyond. The same thing, but now I assume a more realistic network, even though it is still a very academic one. The network is a ring. And all sources are going 2 hops. So I assume there is a source here that is sending 2 hops away, and this light blue that is almost invisible on this display is showing that every flow is going 2 hops. Right? And now, of course, all the flows are using shortest path routing with distance vector, for example. So there is no loop in the path of flows. However, there are loops in the dependency of congestion because the network is a ring. The ring is the simplest of the networks with loops, but we expect all networks, except perhaps for bridge networks, to have loops because we have redundant links. So this is not a purely academic network. It is something we see in practice. How much can a node send to a destination in this setting here? I zoom on source I, then certainly, and I assume the capacity of all the links is C. All the links have same capacity C. Everything is symmetric. All sources have the same rate, so they attempt to send at a rate lambda. Then if lambda is very high, there might be losses. So what is transmitted here is lambda prime on the first link, and lambda second, if lambda prime is still very high, there might be losses at the second router on the path. So lambda second might be less, and then when you go out, I assume here there is no congestion. There is only one flow going here, so what goes out is lambda second. This is what I assume here. If it's easy to see that if lambda is less than half of the capacity in this highly symmetric thing, there will be no losses, because on every link there are two flows. The flow for which this is the first hop, and the flow coming here for which this is the second hop. Then if each of the flows is sending at less than half of the capacity, then the total amount of traffic that wants to go onto the link is less than the capacity. There is no loss. So the answer in that case is given here, lambda second. What goes in is what goes out. Of course, here I am neglecting what happens at the boundary of capacity. If we load a link by 100%, there will be queuing phenomenon that may occur, and there might be losses even though we're a little below capacity. But I'm ignoring this in this very crude approximation here. Now what happens when we're above? When we send more? Certainly there must be losses somewhere, because it's not possible that the two links, that the two flows send lambda, because 2 lambda is larger than C, so there must be losses. We can repeat the kind of maths we did in the previous example. We can see that the ratio of accepted traffic as one node is given by the capacity of the node divided by what wants to go in. So what wants to go into this node is lambda plus lambda prime. And since there is rotational symmetry, it's the same everywhere. So this is the ratio of acceptance. So the loss rate is 1 minus this. Therefore, now I can apply this assuming I have proportion of the same loss for all flows. This will give me what goes out, lambda prime, when I put in lambda. I put in lambda. The lambda prime I obtain is equal to the acceptance rate multiplied by lambda. It gives me equation 1. Similarly, if I want to find what is lambda second, or the lambda second is what comes after this link, on this link, what I'm offering is lambda prime, because the thing is completely symmetric, the acceptance rate is the same, so I have the same formula to go from lambda prime to lambda second. This is relatively straightforward. Now, what is my problem? I know lambda. I want to find what is lambda second. I have this intermediate variable lambda prime, but since I have two equations, I can eliminate lambda prime, and with a bit of maths, I can get lambda second from lambda prime. This is what I did here. We have a quadratic equation to solve, and we obtain here lambda second is given by this formula. I plot this formula on assuming the capacity here is 10. So we see that, the capacity should be 20 here. This is a bar. We see that as long as lambda is less than half of the capacity, then what goes in goes out. So we have this linear thing, and this is what the output will be. And then if we plot this when lambda gets larger, we have this curve that gets decreasing. And if we go in the limit of very large lambda, if you remember your analysis 101 course, what's the limit of this when lambda goes to infinity? Well, you will find that it is 0. So if you go long enough, it is 0. So this network, when lambda gets very large, has 0 throughput, similar to the intersection in Paris. This is exactly what we call congestion collapse. So congestion collapse for this network occurs when lambda is, this is not C, this is the lambda star, the optimal lambda. This is when we go above. Now, in the ideal world, what we would love to do is to have something that, we would like to do this, the red line here. So the blue should be replaced by the red. A few more words on that. Here I have a system. Any complex system has a capacity. Sometimes it's hard to estimate, but it has a finite capacity because we're not superhumans. We can do only things that have limited power. When you're below the capacity, everything is fine. When you're above capacity, you have congestion. You cannot do more than the capacity of the system. That can pump C bits per second, then it will not pump out more than that. If you have a web server that can do 2 million requests per hour, it will never do more than 2 million requests per hour. Now the question is, congestion is unavoidable, you have to accept it, but what you want to avoid is congestion collapse, that it goes down. If you have a server that has a capacity of 10 million requests per hour, when it's congested, you don't want that it serves 0.01 million instead of the 10 million. Right? You don't want that the capacity goes down when, or the performance goes down when it's at capacity. It's very hard to avoid in practice, so any complex system that has queuing or synchronizations, waitings due to whatever reason, will have this. Think of all examples in real life. I've mentioned the road traffic intersection. Think of yourself. If you receive too many emails, you spend a little of time just seeing whether the email is interesting, and at the end you spend so much time seeing that things are not interesting that your output, measured in things you've learned or homeworks you've done or labs you've completed, reduces if you're doing too many things. So that happens for any complex system, including us. So this is the take-home message number 2. Now in the internet, if we do this, if we allow sources to send at whatever rate they want with UDP, with TCP, of course, this is not possible today because TCP has a solution for congestion collapse, then we will have congestion collapse. It has occurred historically in the mid-80s. One day the internet collapsed. In the mid-80s, TCP did not have congestion control. So it had only the bells and whistles we've seen so far. And then there was flow control. Flow control is about preventing the source to flood the destination. But there was nothing for congestion control, which is about preventing sources to the emerging property that would be non-desirable of the network being clogged due to the symptoms of the phenomenon I've just explained. At that time, of course, the internet, you can imagine in 1985, the internet was with links at a few kilobits per second. There were 2 or 3 computers per university, so it was not a big system. Nonetheless, it collapsed. It was not able to work. And the reason was later analyzed. It was exactly a congestion collapse, like in this toy network. So, conclusion, step 2, we need to do something. We cannot simply let sources send as much as they can based on their perception of their local environment and perhaps the window advertised by the destination. So we need to avoid the efficiency, and one way to do it would be perhaps to solve an optimization problem, if we find a way to do it practically, in order to increase the total throughput, for example, of the network. Let's take another toy example. Here I have 3 routers. I have a number of flows, 1 red, 1 blue, and 9 green ones, and they're all trying to send. Right. We've seen that it's not a good idea if they try to send as much as they can, but what if we have the optimal solution? What would it be? In this network, what would be the total throughput? Total throughput, for me, here, is the sum of all the rates of the red, blue, and green flows. So what's the max that can be achieved in this network? 5 more seconds. And the correct answer is 20. Whoops. Well, I admit it's a bit hard to do because it's a linear programming stuff and computers are better than us. So the total throughput is the rate x0 plus x1 plus the sum of the rate of the 9 flows, which, because they're all the same, probably they must be at the optimal the same. So plus 9x2. I assume they're all the same. So I want to maximize this, now subject to the capacities of the links. So subject to, now what are the constraints? Well, on the first link, x0 plus x1 must be less than 10. On the second link, x0 plus 9x2 is less than 10. And the variables are non-negative. So this is a classical linear program. You can ask your preferred linear programming package to solve it. Or you can also do it manually because this is a very simple case. You can see that the total throughput is suddenly less than 20 because of each of the constraints here. So the total is less than the sum of the constraint. x0 appears twice if we sum them. So certainly the maximum throughput must be less than 20. Now 20 is feasible. If I do this, I give 10 to x1 and 10 over 9 to x2, I have a feasible solution. So I have pedestrian proof that the max is 20. Okay. So we know we can solve those things. Now, let's hope we would be able to do it in a practical way with sources that are on the internet. But here, perhaps an intermediate question. What is the value of the rate that is allocated to x0 when we achieve the maximum throughput? So I assume I have an allocation. We have invented the super-duper congestion control mechanism that will try to maximize the sum of the rates. How much will it give to x0? Five more seconds. And the correct answer is none of the above because it is 0. We could look at the solution we had of the previous quiz. If I look carefully at how I have obtained this maximum 20, it is by giving x1 equal 10 that forces x0 to be 0. Still, it's not a complete proof. There might be another allocation that achieves the same optimum but gives something different to x0. And this is what we can verify is impossible. If I consider all the possible allocations that are feasible, equations 1 and 2, and achieve the maximum, equation 3, then it's easy to see that by necessity we will have 9x2 equal 10, and therefore x0 is equal to 0. So it's impossible. It's impossible to do otherwise. Okay, what have we learned on this example? Well, yes?
Why is x1 equal to 10?
Well, you plug this in the rest of the equations. You have x0 equal, you have x1 plus 9x2 equal to 20 with x1 less than 10 and x2 less than 10 over 9.
In the previous slide you said that you put x1 equal to 10. Can you go to the previous slide?
Yes. Here I have given one allocation that achieves the maximum. And this allows me to answer the question, what's the maximum? I'm asking a different question. I say, among all the allocations that achieve the maximum, what do they give to x0? And we see that all of them, there's no other one, in fact, than the one we've seen before. Any allocation that achieves the maximum must give 0 to, so there's only one. But the important thing is it's 0. So it's completely unfair. If you want to maximize the usefulness of the utility of your network, you shut down x0. Why do you shut down x0? Well, because it's too expensive. It's using 2 links. The others are using only 1 link. So if you get rewarded by the total flow in this network, then disable x0. Well, this means we have a problem in defining exactly what we should optimize in a network. We've seen that if we let anybody do whatever they want, we will have problems of congestion collapse or inefficiencies. So we need one solution is to say, well, let's imagine a distributed optimization framework that will allow us to run the network. But the question is, what should we optimize? And certainly we should not optimize total efficiency. Another way that philosophers could put that is that maximum efficiency might be at the expense of fairness. If you want to be maximally efficient, if you want to maximize the total revenue of any complex system, by the way, also society, then you are typically unfair. That's called globalization. That's what happens. In a network, we would not like this to happen. You would not like that when you connect to a web server in California, that you get 0 throughput because you're not interesting for the network. They prefer to serve other flows. And the system would not work. Of course, the internet would not be what it is today if we would do that. So we need to find a way to run a network in a way that is as optimal as it can be. Still remains to be defined how, but also to be fair. So what is it to be fair? What does it mean exactly? So we have, superficially it's easy to say, when you feel you've been handled unfairly, then you can say, yeah, it's unfair. But what would have been a fair treatment? It's not always very easy. Let's try a first definition, which I call egalitarianism, which means we give the same to everyone. We insist that everyone has the same, but the largest possible. So we still have an optimization criterion. We maximize the rate we give to everyone, subject to the constraint everybody has the same. It's total communism, if you want, even though in communism, of course, the members of the party were a bit special and had more. But for the non-communist part of a communist country, this is what is, in theory, happening. In theory, of course, all those things. So, what do you get here? What's the maximum you would give to everyone? Five more seconds. And the majority vote is the correct answer. Oops. This is the correct answer. Again, a linear program. We have to maximize x, which is the same rate given to everyone, subject to the constraints. What are the constraints? Well, now they are simple because they're in one variable, 2x less than 10, 10x less than 10. Then the x is less than 1 and x is less than 5. The first inequality is always redundant. So x is less than 1. What's the max of x subject to x less than 1? We don't need software to find that it's 1. So here is what egalitarianism would give. So egalitarianism gives x equal 1. Okay, I can't write for some reason, but it's 1. But it is stupid, because if you look at the first link, I have only 2 megabits per second used. So of course you nobody would do that, right? In this network, you insist that the first link is not used. We could increase the blue from 1 to 9. That would not hurt everybody. So unless you're extremely vicious and you insist that others don't get more than you because it hurts you, just the feeling that they have more. But in a network, that's not, I mean, you're trying to do things. If the best possible for you is 1 megabit per second, if for others it's better, then let others be better. Plus sometimes you will be the others. So a better allocation, which is as fair in some sense, at least informally, but more efficient, is to give 9 to the guy in the middle, which is now zooming. Okay, thank you. Is to give 9 here. Oh, I get my pen back. And this leads us to, there is a formal way to define this. It's called max-min fairness. So max-min fairness is, in some sense, an optimization criterion where we say we want to be fair, but we also want to be maximally efficient. And there is a theory for that is called max-min fairness. And the max-min fair allocation in this example would be exactly this. What is it in general? Here is the definition. It's a bit more complicated because we want to be able to handle every possible case. So here it is. So I assume I have to allocate rates. Here we think of the rates allocated to flows, but it could be any resources in general. I allocate a vector of x subject to some constraints. So the constraints are by saying I have a certain domain of feasible rate allocations. In the toy examples we've done, all the feasible allocations are given by linear constraints. So we have feasible allocation. And among all the possible allocations that are possible, we've seen that there are many. In the toy example of the last toy example, we've seen 3 or 4 different allocations depending on what we want to optimize, what is the philosophy of allocation we have. So among all possible allocation, I say that one specific allocation is max-min fair if it's impossible to increase the rate of any of the sources without decreasing the rate of another source that is less well off, that is less rich than this source. So in other words, or formally, I have my allocation x. I ask the question, is this max-min fair? In order to know whether it's max-min fair, I will do a thought experiment. I'll say, okay, let me try to modify x. I have a new allocation y. And this y is still feasible and has given more to some source s. ys is larger than xs. Then if this is true for y, it must be true. The price to pay to be able to do that is this one. I must have ys prime less than xs prime. That means I've decreased some other guy s prime. And the guy that I've decreased was not receiving more than s prime, than s. So I have an allocation. I give a number to everyone. Then it is max-min fair if it's impossible to increase someone without decreasing someone who should not be decreased. Because if you want to be fair, why would you decrease s prime if s prime already had the same as s, or even worse, less? So in other words also, we can say an allocation is max-min fair if any deviation that would increase one source will force you to do that against fairness. I admit it's a bit complicated, but let's see on this example. If I apply this definition, what do I get? I propose 2. Well, more precisely, the definition I've given is not a constructive one. I'm not saying here is the way to allocate things. I'm just saying among all the possible ways to allocate rates, what are the ones that are the best ones from the viewpoint of max-min fairness? The best one means they try to maximize everything while being fair. Here is A satisfying this property is B satisfying this property. Close in 5 seconds. And the majority vote is B. Is it an educated answer or a guess? This we will see. But that's the correct answer. Well, I've mentioned orally a few minutes ago that B is max-min fair. And A certainly is not, or otherwise this definition is not operational, because A gives 0 to source 0, so that would be strange if it would be the max-min fair allocation. But let's look at that in detail. So why is allocation A not max-min fair? Let's apply the definition. So I have an allocation that's given here. Let's try to allocate to increase one of the sources. For example, if I increase x0, am I forced to decrease someone that was receiving less rate or the same as x0? Well, it's not true, because if I can increase x0, for example, by moving from A to B, by doing that I decrease x1 and x2, but x1 and x2 were in a better situation than x0. So you've taken, you're like Robin Hood, you've taken from the rich and given to the poor. That's fair, at least in this theory. So A is not max-min fair. I can improve it. I can remove a bit from the rich, 1 and 2, and give to x0. So it's not max-min fair. Is B max-min fair? Well, we need to verify that the condition holds, and we have to verify all possible moves we do from the allocation B. So we need to try and see what happens if we increase x0, x1, and x2. So if we increase x1, in this allocation that is here, so x1 is the blue. If I increase x1, I must decrease, if I increase x0, x0 is the red, which receive 1, then I am forced to decrease one of the green, because the red and the green on this second link are all receiving the same, 1 megabit per second. If I increase the red, and the constraint still has to be satisfied, one of the greens, or if I do it equally, all the greens have to be decreased. This contradicts max-min fairness because the green and the red were the same in my allocation. So if I do that, I do an unfair move. So the property is true concerning x0. If I increase x1 now, x1 is blue, then it's easy. It has 9 megabit per second. To increase x1, I have to decrease the red flow, which was receiving much less, so that's completely unfair. Similarly, if I increase x2, it's the converse of the first case, I have to increase x0. So from any source that I look at the problem, if I try to give more to someone, I have to do a move that's unfair. So I'm stuck in a corner, cannot move from there. I cannot improve this allocation from the viewpoint of fairness. So it is what we call a max-min fair allocation. Now, of course, if we need to do that, yes?
Well, can you talk about fairness if x0, x1 and x0 and x2, okay, they increase one and decrease one, but here we have 1 flow for x0, but 9 flows for x2. So in terms of splitting the results between x1, x0 and x2, we do in a fair way, but if you consider the flows.
That's a very good question. So I said fairness here, and I assume I want to give the same to all flows. So I treat every flow as an individual. Now what happens if those 9 flows are done by the same machine? Right. That's a good question, but there's no good answer to that good question. There's no solution to that. It's impossible in the internet today how many people are sitting behind a flow. whether it's one person or whether you have a tunnel and you have 1 million computers behind it. And that's one of the issues. So fairness is not a perfect solution in the internet today. Fairness is given per flow, and we will see a flow is a TCP connection in practice. Now, if you have 10 TCP connections, you get more than if you have only one. That is true. But we will try to at least to apply fairness per TCP connection. That's all we can achieve. Now, if we want to compute the max-min fair allocation for in a given scenario, first, what I've seen here is not a computation, it's just a verification. I can verify whether an allocation is max-min fair, but first it's pretty clumsy, although linear complexity, but still pretty clumsy. And second, it doesn't tell me what is a max, do I get the allocation B that I had before. Fortunately, there is a very easy way to get it. So, first, there is one max-min fair allocation, and there is only one. This is because the set of constraints is convex. If you take the general problem posed by max-min fairness and you assume the set of feasible x, whatever the interpretation of x, is convex, there are even a few generalizations that go beyond convex, but certainly for convex. Compact, that means it has to be bounded. If some rate can be infinite, then well, there might be problems. Then there is one allocation, max-min fair allocation, and only one. So we can speak of the max-min fair allocation. That's the first good news. And even better, there's a simple algorithm to compute the max-min fair allocation, which is called the water filling algorithm, or the progressive filling algorithm, which is essentially what we did in the previous example to get allocation B. First, we try to give the same to everyone, and we give the max that we can. Then all the rates that are blocked because they use links that are fully utilized, we say that's the max you get, be happy with that. Then if there are other sources that can get more, you will try to increase by giving the same rates to all the sources that still have the freedom to be increased until you hit a limit. When you hit the limit, all the rates that hit the limit, they say, okay, you're blocked now, etc. You continue. It's called water filling because it's like filling water into a complex system of tubes, and then the level will go up the same everywhere, which can be translated by this algorithm. First, you mark all sources as non-frozen. That means you will try to increase them. To increase the rate of all non-frozen sources to the largest possible common value. So give the same common value for all the non-frozen sources. And you mark the sources that use a saturated link as frozen. And you iterate. And because you have a finite number of links, and every step of this algorithm, you will saturate at least one link, and the algorithm will terminate. Not only it will terminate, but it will find the max-min fair allocation. Let's check on this example. We know that B is the max-min fair allocation. Let's check on this example how it would work. Step one, so I have my 11 sources. I allocate the same rate to all. So I maximize T, subject to the constraints that 2T and 10T are less than 10, the constraints of the capacities of the link. And then we find T equal 1. That's exactly what we had done a few minutes ago. Now, at the end of this step, what are the saturated links? If I consider this allocation, 1 to everyone, we see that the second link is saturated, the one with the arrow. So all the sources that go through this link, they are now frozen, which means all except the blue. Now, step 2, I continue. I do the same with all the unfrozen sources. Here it's very easy, there's only one. So you continue to increase the blue until you hit a limit, and the limit is at 9. So at step 2, you give 9 to the blue source, x1 equal 9, and that's exactly the allocation B that we had done before. So before leaving you for the break, can you do the same for this example here, where I have 1, 2, 3, 4 links that each have a capacity C. On every link, there is a big red connection that goes across the entire network, plus one local connection. What's the max-min fair allocation? I close in 5 seconds. And of course, the correct answer is number 1, C/2 here. We do a break and restart in 15 minutes.